Quantum mechanics can be developed in two ways. One is following the Schrödinger prescription, in which a differential equation is formed and subsequently one solves the differential equation subject to the boundary condition. Another alternative formalism of quantum mechanics exists, which is known as the matrix mechanics. In matrix mechanics, one extensively uses the commutator algebra. So, commutator algebra is an essential part of quantum mechanics when one follows the matrix mechanics formalism. Even within the Schrödinger formalism, commutator algebra finds its important role because in many cases the calculation can be made very simple using commutator relation. In an earlier lecture we have derived the first theorem, where in the derivation we have used the commutator relation. If one wants to calculate it exclusively using Schrödinger equation and without using the commutator relation, the derivation would be too much lengthy. This is one thing. Another thing is that the commutator relation is connected to the uncertainty principle. If we have two operators A and B which commutes, then its simultaneous and precise measurement is possible, which leads to the complete set of commuting observables. With this concept, today we shall start the basics of commutator algebra, and probably towards the beginning of this lecture or in the next lecture we shall go into the quantum mechanics of commutator algebra. In common algebra, we know if we have two quantities A and B, then the BA and AB are same, that is to say, this is commutative. But if we have two operators, operator A and operator B, it may not be always equal. These two may not be equal. So one defines the commutator of two operators A and B. The operators are denoted by hats on them. It is defined as A operator B minus B operator A. Obviously, it is found that this is minus B operator A. So, two operators are separated by a comma. Now, if we have more than one operators, then what will be the result? If we have, say, this is the operator, A commutator with B plus minus C. In that case, by definition, it is A operator, B plus minus C operator minus first. If we in the case of operator, the ordering is very important. Then this is if we take these two terms, couple these two terms, this is A operator A commutator B, this comes from these two terms, and if we take plus minus common, then this is A commutator C. So the result is simply A commutes with B, again A commutes with C, This is the simple rule. Without going into proof, I am just writing few such identities. One may be A plus minus B commuting with C. So the result will be A commute with C. So this is AC commutator, and again B will commute with C, but another complicated one may arise like this: A plus minus B, C plus minus D. Here first A and C will commute, A and C will commute, then A will commute with D, AD commutator, then B will commute with C, lastly. Note that this is the sign from there and this sign is from there, and when B and C will commute, then it will be 2 plus minus BD. When both B and D are of same sign, when this is plus, or this is minus, then the sign will be plus, otherwise the sign will be minus. Now I come to the other type of commutator relation, when one operator commutes with the product of two commutator, A commuting with BC. In that case, we first write the relation. This is ABC minus BCA. This is by definition. We write it as A, B, C, subtract a term BAC and add the same term BAC minus BCA. Now from these two terms we take C common from the right, so we have AB minus BA with C appearing from the right, and from these two terms I take B common from the left, and the resulting quantity is AC minus CA. So the result is, this is AB commutator with C appearing from right, and this is AC commutator and B appearing from the left. So the result is simply A and B commutator, AB commutator, C from the right plus AC commutator, B coming from the left. So if we do such thing, another AB commuting with C, then obviously here first term will be A commute with C and B will appear from the right. So this is AC, B on the right, and again C will commute with B, C will commute with B, BC, and A will appear from the left. And another complicated term is this ABCD commutator. We can derive it in this way, but I am just writing the result. First thing, A will commute with C. Then when A commutes with C, B and D appear, and both from the right. So it will be DB. Then A commutes with D. A commutes with D. B will appear from right. C will appear from left. Then B commutes with D. A and C will appear from the left. So lastly, B will commute with C. This should be the third one. I have just sent A from the left, D from the right. So these are the commutator relations. Another interesting type of commutator relation arises like this, which is A b to the power n. By an power of operator, we mean the operator is operated successively n times. So the quantity is A b to the power n. To show that this is n b to the power n minus 1 AB commutator. To prove this, we shall first work out few cases. B square B. So we write it like this. First one B will appear from the left. So and this will be, there will be two terms, so this is simply 2B AB commutator. Or let me, without skipping the term, let me write. This B is written as B operator times B operator. So first AB commutator, B is from the right, B from the right, and then B from the left. So the result is twice AB commutator. If we consider A B operator cubed, then it can be written as A B operator times B operator square. So the result is first AB commutator, B square will appear from the right, then AB square commutator, B will appear from left. This we have just evaluated as 2B AB commutator. So if we add these three terms, we find that this is B square 3B B operator square AB. So we see that this relation is valid for n is equal to, obviously n is equal to 1, 2 and 3. Adopting the method of induction, let the relation be valid. Let A b to the power m is equal to m b to the power m minus 1 AB commutator. That is, we assume that the relation is valid for m. Then what happens to a b to the power m plus 1? We write it as a b times b to the power m. So it will be AB commutator b to the power m will appear from the right and b will appear from the left. A b to the power m operate. This by assumption this is m b to the power m minus 1 AB commutator. So this together with this makes b to the power m, and if we take b to the power m AB commutator common, this is m plus 1 b to the power m AB commutator. So what we see that the relation is valid for n is equal to 1, 2, 3, and if the result be valid for n is equal to m, then it is also valid for n is equal to m plus 1. So the method of induction, as per method of induction, it is valid for all integral n. Let us now come to some few operators which are differential of one very important property that is called the Jacobi identity. Let me first say Jacobi identity, and let me remind you that this is a very important relation, will be used every now and then in quantum mechanics. We consider three operators A, B, C and consider the commutator of this form. A plus B appears from left, then CA in the cyclic order, then C comes and this is 0. This is known as Jacobi identity. Jacobi's identity. Now we come to another. The proof is left as your homework. Now we come to a relation like this. X ddx. So there are two operators, one is x operator and ddx. What is the right hand side? We choose an operand which operates on this. So the result is x ddx operating on psi of x minus ddx operates on, so this is x d psi dx, and there will be two terms. One is x d psi dx, another one is simply minus psi. So these two goes and this is minus psi. So we conclude that x ddx is equal to minus 1. Sorry, minus 1. Consider the basic commutator relation, the xpx commutator relation. This is x minus ih cross ddx in one dimension. So if we take this part common, minus ih cross common, then this is x ddx, which is, this is actually 1 means identity operator. So this is minus 1. So this minus and minus packs it plus. So this is plus ih cross identity operator. Another interesting thing regarding this is that if we consider this to be the basic commutator relation, then in X space we define in X space or in position space we define X operator as X, then one obviously leads to Px operator is equal to minus IH cross del X. If we work in momentum space, then obvious choice is Px operator is equal to Px. Then this basic identity relation leads as X operator is equal to plus IH cross del Px. So this is the one speaks of momentum space operators. Now we come to few other relations involving trigonometric functions or like this. Let us calculate such an operator, x sine of px. Now we know the sine of px can be expanded in a power series as per k starts from 0. This is the expansion of p sine x. So we write it as commutator of x times commutator of this factorial. We take this sum out, so the factor minus 1 to the power k then the quantity that appears is x px to the power 2k plus 1. Recall that a b to the power n, which we have proved is n b to the power n minus 1 a b commutator. This relation we have just proved. So in the case of the x p to the power px to the power n would be n px to the power n minus 1 times operator of x px. This is IH cross identity. So this is IH cross n px to the power n. So this operator, this part is IH cross 2k plus 1 px to the power 2k. So this part becomes k to the power 0 to infinity minus 1 to the power k. This 2k in the denominator, so IH cross taken out of the sum, this makes it px to the power 2k by 2k factorial. This is simply cos of px. So the result is IH cross cos of px. Here we should have proved the operator signs, which is missing in few cases. Similarly, we can prove that the commutator of x cos px. Let me evaluate it. X cos px is equal to summation over k is equal to 0 to infinity minus 1 to the power k 1 upon 2k factorial. Then this is x px to the power 2k. This is equal to h cross 2k times px times 2k minus 1. So the result will be h cross h cross minus 1 to the power k. This makes it 2k minus 1 factorial, and in the numerator we will have px operator 2k minus 1. Now see, if k is equal to 1, this is negative factorial, which is not defined. So we must define k from 1. Since for k is equal to 0, 2k minus 1 is a minus 1, whose and factorial is not defined. So what we do, we can do one thing. Either we can start the sum from 1, or we can make it plus 1. So this is equivalent to h cross note the change. I have to overcome this. One should start the sum with k is equal to 1, and which is equivalent of starting the sum again from k is equal to 0 and replace k by k plus 1. So this is the relation. And this is minus h cross sine of px operator, as we expected them to be. Now I come to few of operators of quantum mechanics specifically. Before going to that, I like to state the basic commutator relation in a compact way. The basic commutator relation of quantum mechanics, basic commutators of quantum mechanics. They are x operating on x, x operating on y, x they are all 0, the null operator, which is summarized as q alpha q beta is equal to 0 always, where q1 is basically x, q2 is equal to y, and q3 is equal to z. Similarly, we call p1 is equal to px, p2 is equal to py, and p3 is identified with pz. In that case, there will be again the commutator relation involving p's px 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 py px pz and such other 6 relations which are again 0. This is summarized in a single relation: p alpha p beta is equal to 0. Now we come to the most important basic commutator relation involving x. We know xpx is equal to plus IH cross identity, xpy is equal to 0, xpz is equal to 0. There are other 6 relations of this sort which can be written as q alpha p beta is equal to IH cross delta of alpha beta. So these are the basic commutator relations. We come to the commutator of x with kinetic energy operator. Now, with this knowledge, we start kinetic energy x with kinetic energy operator. So kinetic energy operator T, the kinetic energy operator Ke operator is equal to p vector operator square by 2m. This is basically 1 upon 2m px Now we find the commutator of x with t. So x with t, because it becomes 1 upon 2m taken out, and then x operator operating on px square plus py square plus pz square. This commutator will, so it will be sum of 3 commutator relations: x with px square, x with py square, and x with pz square. As for the relations, we have just stated this, and this is the only non-zero term, and this can be written as 1 upon 2m. This is xpx, and px coming from once from right and once from left, so this is 2, there is 2, and this part is IH cross. So the result is IH cross px operator by m. Similarly, we find that yt is equal to IH cross py by m, and zt is equal to IH cross pz by m. So now I come to this commutator relation: all vector operator and this thing. This part is I cap x operator plus j cap y operator plus k cap z operator. This is part times t operator. So this can be written as I cap, the unit vector, xt plus j cap yt plus k cap jt. Note that this is px by m, this is py by m, this is pz by m, and obviously ih cross is there. So this is ih cross m p vector operator. Another interesting property is the one trivial case is p vector operator of and t, this is 0. This is because x to the power m, x to the power n, this is 0 for any operator x. Another interesting case would be the commutator of x with potential energy V, which is, I am going to now describe the in some calculation one comes across the evaluation of this type of operator, x operator commuting with v of x. Now the operator v, since it is a function of x, one can expand it in Taylor series and we write it C0 identity operator plus C1 x operator plus C2 x square operator plus C3 x to the power cube operator, and so on and so forth. So obviously we see that when we consider the commutator of x with v, the all term goes to 0, so this is 0. It is a trivial case, as we have seen that the operator p commutator of p with t is 0. So the interesting case would be the commutator of p with v. The case will be, let me write it in a compact way, k is equal to 0, C0 x to the power k, with we identify x to the power 0 operator is identity operator. So we write it as, let me say px specifically. C0 is a scalar taken out, it's not an operator, so it is px operator x operator to the power k. So this result, we know that this is k, this is k x to the power k minus 1 px x commutator. This is equal to minus ih cross identity. So this is minus ih cross k x to the power k minus 1. So the result is minus ih cross, it is out of the sum, then ck k x to the power k minus 1. Writing explicitly, this becomes minus IH cross minus IH cross, then C0 with null operator plus C1 plus C2 plus 3C3 x square, and so this is basically the derivative of this function of this expansion with respect to x. So we write it minus IH cross del x on summation over k is equal to 0 to infinity ck x to the power k, that is this is minus h cross del v operator del x. In this expression we haven't explicitly used the operator form of px, but we have only used the basic commutator relation, that is x px is equal to IH cross identity. This relation is valid position space as well as in momentum space or any other space we use. Another way of deriving it, which would be much easier, but the derivation is specific to the position space calculation, an alternative derivation of this, but remind that this calculation is valid only in position space. In position space we write psi of x, one-dimensional problem. So this is equal to minus IH cross del x. So minus IH cross is taken out. So this is del x, v of x operating on psi of x. So this is minus IH cross. This is del x v psi minus v del x psi. It will have two terms. One can del v del x term survives, so minus IH cross del v del x times psi. So from these two relations we conclude that px v of x is equal to minus IH cross del v del x. But remember that this is valid only in position space, but the earlier derivation that we have made is a general one and is valid for any space. In the next class we shall consider the commutator algebra, mainly involving the angular momentum operator.